Right, thank you very much. Thank you for staying to the late afternoon. So this is joint work with my wonderful co-author Alex Teytelboym of Oxford. Let's see. Work. Okay. Okay. How many of you have seen this picture before? No. Okay. What is it? All right, so this is allocations of spectrum band in the US to different identities. And it turns out that this is not very efficient allocation of spectrum because there's a lot of band that is not used and should be rather used by commercial services. And in 2016 and 17, the FCC decided to reallocate this spectrum band from TV broadcaster to commercial services. And in order to achieve maximum achievement, this auction around such that they want to find the market clearing and a competitive equilibrium for these reallocations. Now, an allocation that is based on competitive equilibrium is not unique to the world when we have transfer. When money is not allowed to use, we also have this we call pseudo-market scenarios, where we give agent tokens and compute on competitive equilibrium for this agent trade. Okay, so examples are allocating food to local food banks or cost allocations and a lot of others. Okay, so market-based resource allocation is popular in market design because the competitive equilibrium is efficient, is in the core, it's very easy to explain and very transparent. So the literature in market design really focus on kind of two different models. On one hand, we have the transfer utility world. On the other hand, we have the pseudo market. Okay, so this is heavy slide, so let me kind of go slowly on this to get used to the notation. So there will be a set of agents in this model, and each agent J, there will be X. J is a set of consumer bundles for this agent. Okay, these are bundles of goods. Now, for each of these bundles, if I look at the transfer utility economy, the price of that bundle is just simply P times that vector Xj. And the utility is that value how much I value this bundle minus the total price that I have to pay. And the demand correspondent would be that given this price P and my valuation Vj, what are the bundles that I can choose to maximize my utility? Okay? And the competitive equilibrium would be a pair of price and allocation so that everybody choosing their best bundle and market clear. Okay? So market clear, it means that the total consumption is at most the supply, but whenever we have a positive price, they have to be equal. Okay? And it's a big question in literature that when is it that we have a competitive equilibrium, right? And it depends very much on the class of utility functions that we have.
Sorry, the space of bundles is indivisible goods.
Yes, that's right. Yep, yep. I missed that. Yeah. So these are all indivisible goods. Okay. So on the other hand, we have the pseudo market scenarios. So in order to have a reasonable pseudo market, we have to allow randomizations. Otherwise, there's no chance. Okay. So now we're going to relax that by allowing agents to consume lotteries over bundles. Okay. That is L of Xj. And for every price and every budget, so the payment will be the expected payment for that lottery. And every agent is going to kind of focusing on maximize that expected payoff, which doesn't have money here, right? Just like what should be my average valuation over this lottery. And a random demand of the agent is therefore looking for all lotteries. Which lottery give me the maximum expected value subject to my budget? That makes sense? Yeah.
Are you restricting budgets to be the same, or can they be different?
Can be different. Every agent will have a different budget. Okay. A special case of which is equal budget. Okay, so luckily, if we do these randomizations, we have a notion called random equilibrium, which is a pair of price and series of lotteries, one for each one, so that everybody lottery is going to be in a random demand, and in expectations, market clears. Okay, so very nice that random equilibrium exists, but the problem now becomes that it's not always realizable, right? I have a random equilibrium, but I cannot really implement it at the lottery over joint allocations of everybody. Okay, so let me just give you a quick example. Why is that difficult? So here is me. I'm interested in a bundle that contains the car and the tool. My wife interested in the car and the key, and my kid interested in the bundle containing the tool and the key. And in this random equilibrium, all of us get 1/2 probability of each bundle. How are we going to allocate this, right? So there's option one. I'm going half of the time I get the car and the tool, and my kids get the key. Okay? Half of the time I get nothing. My wife get the car and the key, and the kid get the tool. Right? My kid's going to cry if I implement these options. So similar, if I implement option number 2, my wife's going to cry. Okay. Option 3 and 4, similarly, right? So I'm going to cry in option 3 because I get the car half the time and the tool half of the time separately. And option 4, everybody is going to cry. Okay, so there's no way that you can implement this random allocation as lottery over the real allocation that we want. Okay. So therefore, the literature has really looking at these questions of 2 different markets in a separate 2 questions. So question 1 say that what class of preference that guarantee the existence of competitive equilibrium in TU market? And then question number 2, what class of utility where we can guarantee the realizability of random equilibrium? Yep.
Can you clarify about realizability? In the previous example, what's wrong with these? So you're getting the probabilities.
Yes, but not realizable because, for example, in this case, my kid is not very happy. He really wants both the key and the tool at the same time, not separate.
I have utility over bundles.
Yeah.
Okay.
Right, yes, but he might be happy if his utility is additive, right? So it's not always okay. So the question is, what class of utility is it that we can implement such thing? So here is our answer. So actually, we're doing it wrong, inefficiently. We shouldn't add these 2 questions separately. The main theorem said that under invariant class of utility, 2 questions are equivalent. Whatever conditions that we got for question 1 going to imply the same class utility for question 2 and vice versa. So the consequence of this theorem saying that, okay, we can now connecting known results from one word and translate to another, and we can have new application, new results as well. And there's a lot of maximum domain results that existed in the literature. Now we can transport in that other words as well. You had a question, Nick?
For question 1 above,
Yep.
is the issue due to not allowing randomization? Or
Yeah, right. Question 1 doesn't allow you to randomize.
if we allowed me to randomize between bundles in my optimal set, does that resolve any of the existence issues, or do they remain?
No. Yeah, so actually, right. So question 1, so existence of equilibrium TU world game can be captured by this linear program, and existence of integer point and should be coincide with the optimal fractional solution. So the 2 questions can roughly the same if you allow randomization or not. Okay, so here's the implication. So there's various results in the literature in both of these worlds. So for TU-GRAM, we have the unit demand, sharply shooting, and in pseudomarket, we have the famous Highland Zeckhausen. Now, because of equivalence, we know that they are the same results, right? Similarly, for additive substitute, for example, Casual Crawford showed that substitute valuation guarantee exists in equilibrium. And a recent paper of Wu, Ferrasang, and Zhang, and also with my co-author Vora, that's 2 separate questions, 2 papers, we show that in pseudo market they can also be realized. So that for other class of utility, when we know there exists a competitive equilibrium TU game, but we don't know for the pseudo market, now we can translate those to get new results. Yeah, any questions so far? Yeah. Very cool. Some of you, if critical, you might, is it too good to be true? Here's a counter example, right? Again, go back to that example. So assume that I have this sort of utility functions. My kid value these bundles as 2, and me and my y value bundles 0.9. So this would be a competitive equilibrium. P is 1 for the 2 and 1 for the key, and my kid's going to get it. But if I take the same valuation that I took to the pseudo market there, here is a pseudo random equilibrium, and I cannot implement it. So what is missing here, right? So the missing conditions lies in the fact that we need following. So we call a class of utility is invariant. If I take any function inside this class, and I take any vector A, this is M is number of goods, okay? For every good, I have a constant, and I add that additive function into the valuation. That valuation should be in the class as well. Yeah, so I call it kind of invariant according to my constant on alpha function. Okay? So the theorem said that if V is an invariant class of valuation of profiles, then competitive equilibrium exists in the TU economy if and only if every random equilibrium in pseudo market can be realized in the same class of it.
A has to be positive or
So no, they can be anything.
it has to be negative in A?
Yeah, it could be. Yeah. Okay, so the counter example here, why is that true? Because if I add one value plus 1 for the 2 and only to my valuations, this become a new set of valuations, and there's no equilibrium in this case anymore. So that's why this example breaks down when we consider the invariant class of utility. Cool. So why is invariant class is natural? So obviously unit demand is invariant. You have unit demand, you add anything on it, it's still unit demand. Additive valuation is invariant. The psi consistent tree valuation is also invariant. Substitute is invariant. It's a little bit not trivial to see here, but the fact that substitute preferences are really defined in the language that given any price, the demand have to be something, right? The demand is I increase price, the demand of other doesn't decrease. So the fact that in any quasi-linear utility, if I have a defined property based on the price, it's equivalent to shifting that utility in the valuations, right? So any class of utility that can be kind of defined in the language that at any given price vector, the demand or the payoff satisfy, blah, 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 that is also in an invariant class. All right, 5 minutes, so it's very quick. Ideas of how we prove it. This direction is relatively easy. So if we know that pseudo markets can be realizable, then there should be a competitive equilibrium. The reason that we do it is that I'm going to take a convexified equilibrium, what Nick suggested, and then I'm going to transfer it to be a random equilibrium of the corresponding economy. And because of my assumption that that random equilibrium can be realizable, then I'm going to take that realizability and translate back to a competitive equilibrium in the discrete sense. This direction is a little bit more difficult. It said that I'm going to take a random equilibrium. In step number 1, I'm going to use linear duality and transport that into a TU world with a different utility, not the same, but it's kind of a different utility. And then using my assumption here that competitive equilibrium exists, I'm going to perturb the utility a little bit to ensure that I can implement that equilibrium as a log 3s over other comparative equilibrium. And that log 3 is going to go back here to give me the feasibility, the realizability of random. Okay. So there's several extensions in the paper. I can look at constraint economy. So instead of a budget constraint, I can have an arbitrary linear constraints. So you can think about this as auctions when advertisers have some sort of total budget on different regions or different kind of ads can be captured in this case. Or you can have a pseudo constraint economy where I can have a diversity constraints in this economy as well. So the summaries of the papers, we have got to give you 4 theorems really. I think that competitive equilibrium exists in TU economy in invariant class if and only if any of these random economy can be realized. Again, so the conclusions of this paper is that hope you convince you that these connections between TU world and pseudo-market is powerful. It creates a lot of new results and unify the things that we knew before. And there's a couple of questions for future works. Hopefully we can find more applications. We can move this to an approximate implementation, approximate equilibrium, or even in the world of ordinal preferences as well.